Okay, so here we go with chapter 19, day 1 video. In class we did the activity where we sampled the pennies and we were looking for the proportion of pennies from the 1990s. We took our data, we said let's be 95% confident, so we decided to go plus and minus 2 standard deviations away, because general 95% confidence. So what we're going to do now is we're going to look at, in general, the formula and how do we use it for a general setting. So, confidence intervals for proportions. A confidence interval is what we calculated, and we start out with some p hat, which is our proportion from data. And that interval involves a p hat plus or minus this piece. Now, for our problem with the pennies, we used 2 here because we wanted to go 2 standard deviations away from the mean. In general, we use z star, which is like our critical value. We call it the critical value. It is how many, or the number of standard deviations away. So, for a given level of confidence. So this value changes with our level of confidence. So if I say I want to be 95% confident, well, that's about 2 standard deviations away. I want to be 99.7, 3 standard deviations away. I want to be 80%. Well, I don't know what that is, but there's some sort of number away that we need to be. So in general, we use z star, which is that critical number, which is how many standard deviations away we will be, depending on our level of confidence. And how many standard deviations we need to be. And in class, we talked about a vocabulary change. We're going to use SE, meaning the standard error. And the standard error, we used a little p hat here, because we're talking about for proportions for this problem. So the standard error of p hat, again, is this formula p times 1 minus p over n, all into the square root. And because for this problem we don't know the true proportion, we only know the proportion from data, we use p hat in the problem. We'll talk about where we're getting this critical value in a little bit. It comes from your book, from page A80. We'll look at that. It comes from the back of the book. All right? This part of the formula is what we call our margin of error. It's how much we're going to add and subtract off from our p hat. You watch polling. Certain percent favor the president, plus or minus 3%. That's the margin of error. The margin of error is this part of the formula. Okay. Just like before, if we're going to talk about z-scores and we're going to talk about normal calculations, we have to check conditions or else we can't use this process. Here's the good news. The conditions, same as before. Randomization or representative sample, independence, or the population greater than 10 times the sample, and n times p greater than or equal to 10. Here's the slight change. I don't know the true proportion, so when we do the n times p, we have to use our p hat value instead. Because we don't know the true proportion, we can only use what we have available to us. And then here's another thing. Instead of saying it's okay to use the normal curve, we're going to be more specific now. What are we doing? We are doing a 1 proportion, because that's all we're measuring is 1 proportion. Z, because we're using z-scores for our critical value. Confidence interval. So how do we say that? We actually say that we are doing a 1 proportion z interval. Okay? We say it's okay to do a 1 proportion z interval. So that's why we're going to change the way we say what we're doing. Now we're being a little bit more specific. We wrote a conclusion in class for the pennies. We said we were 95% confident. that the true proportion of pennies from the 1990s were between, well, I don't know, maybe it's 10 and 35%, whatever your classes came out to be. In general, we use this. We are blank percent confident. So whatever that percentage is, whether it's 95, could be 99, it could be 80, just depends on what the person running the test wants to run it at. Confident that the true proportion or true percentage, either one, of what were we trying to measure is between blank and blank. So we set this up, fill in the blanks. For our penny question in class, we said we are 95% confident that the true proportion or true percentage of pennies from the 1990s is between, and then we got like, I don't know, 10 and 35%, something like that. Now, one other thing that we kind of touched on in some classes, but maybe not your class, was what this means. The meaning of a blank percentage confidence. So what does this mean? Well, if we took repeated samples by the same method, okay? So, let me get my pennies. Remember, we did one. We reached in here and we pulled out a handful of pennies. Okay? If we took repeated samples by the same method, so if we could, and a lot of times we don't have the money or the time to do that, but if we could do a repeated sample by that same method, and we made intervals, and we kept making intervals and intervals and intervals, okay? Whatever confidence we're working with, what we say is that percent of those intervals should capture the true percentage of whatever it is that we need. So let me apply it to the problem that we had in class. We did 95% confident. So the meaning of 95% confident. If we took repeated samples by the same method, not changing my method, 95% of the intervals should capture the true percentage of pennies from the 1990s. So watch. So we did an interval in class, and some of the classes saw this and some we didn't quite get to it, but we did an interval in class. Here's your p-hat right in the middle. And we added and subtracted 2 standard deviations away, and we got boundary, I don't know, 10 to 35%. If I made us reach in and do it again, I might, well, I can definitely create a new interval. Will it be exactly this interval? No. If my p-hat moves oh so slightly, my interval's going to move. The width of my interval is going to be similar because I'm going the same number of standard deviation. So now it might look like this. And if I did it again, put the pennies back, mix them up, did it again, it might look like this. Again, there's the p-hat. And I did it again, it might look like this. And I do it again, it might look like this. And I do it again, it might look like this. And I do it again, it might look like this. And I do it again, and it might look like this. Well, that's not it. And I have a whole bunch of confidence intervals. If we took repeated samples by the same method, okay, we do it again and again and again and again and again. Same method, same sampling size, everything's the same. All right? If I'm going to be 95% confident, then 95% of the intervals should catch the true percentage of pennies from the 90s in this case. Well, I'm going to put a green arrow down, or a green line down. Let's say this is the true proportion. We don't know what it is. Remember, we said we'll probably never know it? Well, let's assume it was here. Did all of my intervals catch it? No. Not all intervals will capture the true proportion. Some will miss. Why? Because we have set it up such that 95% should catch it and 5% will not. And I'm willing to live with that 5% amount of error. But that is the meaning of 95% confidence. If we took repeated samples by the same method, 95% of those intervals should capture the true percentage. If I want to get this one to catch it, I might have to use 99%. Well, yes, now 99% of my intervals, every interval is going to be a little bit wider. 99% of those intervals then would catch it. But I don't want 99%. I don't need an interval this wide. I'm comfortable with 95%. And so that is the meaning of this. So when we do a problem, not only are you going to have to find the interval and write a conclusion, many times they'll say, could you tell me the meaning of this level of confidence? And you would write this phrase. Okay? Now, a couple things. If you want to decrease the margin of error, so you got p hat plus or minus a certain value. The plus or minus part is your margin of error. Without changing the level of confidence. So remember I said if you say I want to be 100% confident, well you got to make it wide. But I want to bring this in without changing my confidence level. You need to increase sample size. So if we go back to this formula, okay? If I don't change this number, because that's my confidence level, how can I get this number to be smaller? Well, remember, it's made up of the square root of a fraction. If I can make this number larger, the fraction becomes smaller. The square root of that fraction then becomes even smaller. So, to make this margin of error shrink without changing this, I can create a smaller standard error by bumping up my sample size. But just like before, if I want to go up, if I want to decrease by a factor of 3, I got to ramp up my sample size by a factor of 9 because I'm taking the square root of it. Now, for our data, we wanted to be 95% confident. Okay, we need a Z star for 95%. You might say, well, Mr. Pat, we use 2. Rule of thumb. It is a rule of thumb, but it's no longer what we're going to use. We're going to be more specific, a little bit more precise. So if you turn to page A as in apple 80 from the back of your book, you'll see at the very bottom, it says confidence levels. And you'll see it says 95% or 0.95. The first line above it, you'll see this number right here, 1.960. So now, from now on, anytime we talk about being 95% confident, we're going to use 1.960 instead of 2. It's a slight change. And that's from what I've talked about where the rule of thumb is not quite exact. So this is 1.960. All right? So if we go back to our data for our pennies, notice I'm going to make a slight change. I'm going to use 1.960 here. All right? So our p hat, this one class was 0.17. Some of you had 0.22. Some of you had 0.235. Okay? But the biggest change is instead of 2, we're going to use 1.960. All right? And so when we come back to class, we will use 1.960 with our data and just look at a slight difference in the answer that we get. All right? That's it for chapter 19. When we come in, we're going to do some problems working on that.